All right, let's get started. Today we have Shiva Soleimany, a master's student here at U of A, and she's going to tell us about improving sim to real transfers using computational creativity.
Okay. So, hello everybody. Thank you for your time. Today I'm gonna present the tea time talk. It's about improving sim-to-real transfers using computational creativity. I'm a master's student and I work with Professor Matthew Taylor. Okay, we know that one of the most common applications of reinforcement learning is in robotics. And when we are trying to train an agent for a robotic task, we have two options, whether we can choose to train the robot directly on the real world environment, or we can choose to train it on a simulated environment. If we choose to train the robot on the real world environment, it's good in some ways but bad in some other ways. If we choose that, we have no reality gap, so when we make an improvement to the algorithm, we can be sure that the improvement actually applies. And also there is no need for content creation, by which I mean we don't have to create different experiences in order to train the agent. But training in the real world environment is expensive, which means that we have to worry about things like the robot battery is also very slow. And due to the exploration, it can be also dangerous. For example, if we are training a collision avoidance robot, the agent has to experience collision in order to learn to avoid it. And we cannot always afford to possibly damage the agent. That's why training in a simulated environment is very desirable for us. And although we have the reality gap, which means any difference between the simulated environment and the real world environment, and although we have to create content and it can sometimes be expensive, but since it is safe, it is cheap, and it's fast, it's very desirable for us. So we choose the for many tasks we choose to train on a simulated environment, and we try to improve the performance by different approaches. One approach is to improve the simulation environment and try to make it as close as possible to the real world environment. Although there has been many progress in this area, but there is still much to do, and we have to pay attention that as we make the simulation environment, try to make it closer to the real world environment, it can get very complicated and it's a slow process. The second approach is try to reach a robust control process. So a robust control policy is a policy that can perform well in a wide range of environments. But the downside to this approach is that we have to at least interact with the real world environment through one phase. And the third approach is to use multiple simulators. The idea here is that maybe if we train the agent in different environments, it would be more ready and perform better in the real world environment. But one possible downside to this might be catastrophic forgetting, which means the agent, when it goes to the second environment, it might forget about the things that it have previously learned. One other approach is the adaptive methods, in which the agent tries to learn the transformation function between the real world and simulated environment, but it's given a period of time in which it can interact actually with the real world environment, during which it tries to learn what's the best action to take in the other and later real world environments that it encounters. One of the most common and famous other approaches is a domain randomization, in which we intentionally make the simulation environment harder in order to make the agent ready for learning in the real world environment. And the last approach, these are only some of the approaches, there are some other approaches. And the approach that we are going to use is adversarial approaches. So in adversarial approaches, you have two agents that are interacting with each other. The goal here is the same. We're trying to reach a robust policy. For example, for a walker 2D, we wanted to be able to walk on ice if it has previously learned to walk on carpet. Some people might argue that why don't we just go ahead and learn different policies for different parameter settings, but that would be infeasible because the parameters are not discrete, and we might face an infinitely large space of parameter settings. So we would instead use an adversarial approach and try to make the simulation environment harder in order to improve the real world performance of the agent. So we have two agents, adversarial agent which generates simulation environments, and a learning agent which tries to achieve the main task while avoiding being disturbed by the adversary agent. And the setting is usually zero sum min max objective function, which means in each round either the adversary agent wins or the learning agent wins. So when the adversary agent wants to generate simulation environments, there is different ways. One way is that it can choose to poke the robot, which means it can, for example, simulate different frictions by applying different horizontal forces to the robot, or it can actually change the friction in the environment. Other questions that we have to answer for the adversary agent is that how long is it gonna let the learning agent to stay in each environment setting, so we can optimize over both different environments and how long we're gonna stay in each one of them. But here we only optimize over different environments for now for the sake of simplicity. Another question is that adversary agent, can it see the learning agent brain directly? Can it access what the agent knows so far? And if it can, then it can use that information and knowledge to mess with the agent even more. And also we want to know if we are choosing to create new environments, can we also poke the agent and apply disturbing forces to it too or not? So adversary agent is also an agent like the learning agent, so it must have an action space. What's its action space? The naive way would be to give it the same action space at that as the learning agent, in which case it would be like a driving a student and a driving instructor fighting over the steering wheel. But we can choose some smarter ways. For example, the adversary agent can force the learning agent to learn in the weak points, or we can also give it superpowers, which means the adversary agent can change the environment setting at any time that it wants. What we want to do in this project is to enable the adversary agent to use its superpowers to create creative environments. So what do we mean by creative environments? So the computational creativity is the intersection of artificial intelligence and creativity. One of the approaches to creativity is to use combinatorial creativity, which means we use the combination of previously established concepts in order to reach new concepts which we might not have normally reached. For example, combining the concept of man and wolf would give us the concept of a werewolf. Professor Matthew Gazel have previously worked on using combinatorial creativity in order to design different game levels, and we hope to use this combinatorial creativity in order to design different environment settings. So we are talking about computational creativity, but how can we measure the creativity of each environment? One of the three common measurements of creativity are novelty, surprise, and value. Novelty, there are two types of novelty, which is personal novelty and historic novelty. Personal novelty, the agent says, I have not done this before, while in historic novelty we say it has never been done before. A surprise is different than novelty in the sense that if we saw a token only once over the past 1,000 steps, if we see it again, that would not be novel, but that would be surprising. And we have a hypothesis that maybe surprising environments might protect the agent about possible catastrophic forgetting. And the value of each environment is defined based on the task that we are trying to reach. So the environment that we use is Mojoko or Hopper, which is this one, a robot that is trying to jump forward. And the base setting for it is gravity of 9.8 and leg size of 0.6. So our MDP star is the real world, or our real world hopper. Each is the hopper with the base setting, and we go forward and change gravity and leg size in order to create 15 other MDPs. So one might argue that is it okay that we are using simulation for both our simulation environment and as our real world environment, and we argue that this approach has many benefits for us. One of them is that we can make the environments as far or as close as we want from each other, which is not the case for the real world. And also, each environment can be very close to the real world environment, but they are never perfect. And all models are wrong, but some of them might be very useful. So that's why we are allowed to use simulation for both of them. So here we see the lowest leg size with the lowest value for gravity and the highest leg size and the highest gravity. We can see the left one can move around much more freely. So for our experiments, I think we have 3 phases. In the first phase, we train and test the agent directly on our MDP star. This would be at one of our baselines. In phase 2, we train the agent on each one of other 15 MDPs. We pre-train it, and then we train and test it on our MDP star. And in the third phase, we train the agent half the time. We pick 2 MDPs, train the agent half the time on one of them and half the time on the other one, and then test and train it on our MDP star. So we have 2 benchmarks. One of them is training on the real world from scratch, and we also hope to compare our method against other transfer improvement methods. Our goal during these experiments is to get a sense of what the helpful environments have in common. And is it better to train the whole time on one of the simulated environments, or is it better to train half the time on one of them and half the time on the other ones? What we are looking for in order to define whether pre-training is successful or not, one of them is jump start, which means how well the agent performs immediately on the real world environment. Another one is learning speed. So because we are not training for infinite time, it's important for us how fast the agent converges. So these are the results we have so far for 16 MDPs, which includes the 15 different parameter settings and our MDP star. As we can see, learning in some of the environments is harder compared to other environments. And here we can get a sense of how increasing the leg size affects the agent performance in different gravity settings. So when the gravity is high, increasing the leg size worsens the performance, while when the gravity is low, increasing the leg size improves the performance. So this is the average reward over a million steps for each of parameter settings. This is our base parameter settings, and this is the average reward on each of other 15 parameter settings. So I want you to remember this number. This is the average reward when the agent learns from scratch in the base environment. So this result is a little tricky. The green line is the agent's performance learning from scratch in the base environment. So all of these green lines are the same. And the blue lines are the agent's performance on the base environment when being pre-trained on these 15 other environments. So for example, this one, the agent has been trained on the base environment twice. And this one, the agent has been pre-trained on this parameter setting and then tested on the base setting. As we can see, pre-training on some of the environments is more helpful than pre-training on other ones. This is the average jump start when the agent is pre-trained on each of these environments. As we expect that we have the biggest jump start when we are training in the same environment twice. And this is the average reward in the base environment when being pre-trained on the other environments. So we can see that sometimes pre-training the agent on a different environment than our base environment is actually more helpful than pre-training it on the same environment twice. And as we can see that pre-training the agent has always improved the performance. So all of these numbers are bigger than 2300, which was our average reward in the base environment. So we have some insights and some conclusions here, but we don't have enough data to support them yet. These are just insights for now. Our first insight is that training on the most similar environment to the real world environment is not actually, might not necessarily give us the best performance, because in the red square we have actually trained the agent twice on the base environment, but we can see that we have better performance when we have pre-trained the agent on some different environments. So maybe pre-training on the most similar simulation environment is not the best option always. Insight 2 is that we have the biggest jump start when the similarity of the environment is the most with the real world environment. We can make some conclusions based on this data. One conclusion is that, okay, pre-training on different environments obviously gives different performances. So pre-training in one environment might be better than pre-training on another environment. But we have to pay attention to one thing, is that maybe the reason that pre-training on another environment which is not totally similar to our real world environment is better because we are not training for infinite time. So maybe pre-training on an easy environment improves performance better because the agent was able to learn more in that amount of time in that easy environment. So we have to look out for that. So we want to find the things that the most helpful environments have in common, and we are hoping that maybe computational creativity is a good lens to find out what the most helpful environments have in common and how we can leverage that in our benefit in order to design the best simulation, the most helpful simulation environments. So, any questions? Thank you for your time. How long did it take? Okay. It took
Shiva,
less than 20 minutes.
thanks for the talk. So the two main takeaways that you mentioned were that uh, the the biggest jump start is when the pre-trained environments are similar to the final environment that you want to test on, and the other one was that uh, it is not necessary that a similar pre-training in a similar environment might lead to better asymptotic performance.
Yeah.
Right. So it might lead to a good initialization, but not uh, better asymptotic performance.
Yeah. But these data are only for one run. So we cannot be very sure about the results, but
okay.
That's what I have suspected.
Can you show those plots again for, not the plots,
Sure.
at least the numbers for um, the pre-trained, the first experiment.
First experiment is running each environment from scratch. This one?
Yeah, so this is fine. The one in which you're showing the results for where the conclusion was that uh, pre-training in similar environments might not result in the best asymptotic performance. Right.
This one. No, this one.
Yeah.
Yeah.
So one way you could think about this would be as a curriculum learning problem, that I've got some final task and I just need to pick the task or tasks before. One of the things we've been struggling with is typically in sim to real, you have basically infinite compute, right? And then you for the simulator, and you only really care about the performance in the real world. But in practice, you've got some limitations. You cannot run unlimited simulations. So how do you figure out which simulations you should run? How do you figure out which tasks you should run? And hopefully there will be some benefit to using these ideas of creativity to figure out which of the infinite number of simulations you could be pre-training on, which of those might be most useful.
Right. And so maybe could you repeat the computational creativity angle to this? That how do you envision that would be helpful in this pursuit?
Excuse me, I didn't catch your question.
Right. So I was just asking that. So based on what Matt said, that these are some preliminary investigations in trying to figure out that if you have limited simulation budget, what kind of simpler environments do you want to, pre-train the agents on before they move on to the final task? So you showed us experiments on environments where you change the leg size and the gravity. Um, so I was wondering what the computational creativity angle to this is. Like, what does it
Yeah.
add to this? Yeah.
Okay, so now we are pre-training only on one model, so the concept of novelty doesn't apply that much because the agent previously has only seen one environment. But we are hoping as we pre-train the agent on different environments, maybe we would see that it performs better when it's trained on novel environments or surprising environments. So we are hoping that maybe what the most helpful environments have in common is their creativity, because they can cause the agent to converge to a more general policy possibly. And if that's the case, we can use that in our benefit in order to design new environments that have high creativity.
And in addition to environments having high creativity, you could think of these different environments engendering different policies. So if we were able to pick the gravity and the leg size so that the hopper quickly learned to do a backflip that we had never seen before, man, that's pretty cool. That could be useful, or at least it's different. But this is absolutely speculative. We are hoping that this novel way of thinking about the changes will help us come with a new way of doing this, figuring out how to do this sim to real curriculum stuff.
Cool, thanks.
Hi, Shiva. I guess hearing about this has also made me think of like a high-level question. When we're talking about sim to real, often it's you're trying to model the simulation as close as possible to real life. But now you're discussing how we don't need to worry about making a simulation like real life. We can try changing different aspects of the environment. And I guess I wonder, how often do you think policies are actually dependent on specific instantiations of the environment? Like, you can imagine, you mentioned the factory setting. I'm a robotic arm. The policy for dealing with, let's say, something that's more brittle, and like, let's say there's higher gravity and objects are more brittle. The way you grasp something in a factory floor is you could kind of imagine would be fundamentally different than the optimal setting given the world we live now. So I guess I was just curious, like, how often do you think policies are like dependent on the specific environment instantiation?
I think they are dependent enough for it to be worth looking into it. For example, as you can see here, the parameter setting has a big effect on the amount that the agent learns, especially because we are not training for infinite time. It's where I think the parameter setting has a big effect on how much the agent can learn in that given period of time, and we have to make the most of it. And it's important to find the best parameter settings in order to make the agent learn as much as it can.
I guess what I mean is just, is there a concern that by testing on different parameter settings of the environment, to be robust enough to work in different parameter settings means it is bad for you to have the optimal setting for the real life setting? So factory floor, like you wouldn't, if you're testing on samples where it's like the object you're trying to grasp is too brittle on high gravity, like that would actually be detrimental to you learning like the proper way to grasp an object, like potentially. I don't know. It was just that's what I was trying to say. But I could see it sort of worrying over nothing.
Well, if we have infinite time, it would be the best to learn on an environment that is exactly same as the real world environment. But we are not training for infinite time. So I think in a way, we would never reach the optimal policy, converge to the best policy in this infinite time. So that's why I think it's better. It's not always the best option to train on the simulation environment that is the most similar to the real world environment. I don't know.
Okay, thanks.
That
No,
answers
that
your
answers it.
question.
Yeah, that answers it. Thanks.
I think another way you could take Matthew's question potentially is, what if the brittleness of the object is critical and the brittleness is not something the adversary can change? So if our robot needs to handle different levels of friction and we never try simulations with different friction levels, is that going to completely make us fail? Or is it possible that we just come up with the superset of all the possible knobs that the adversary could turn, and the adversary figures out what is the most novel or surprising?
Okay.
Was that a long enough awkward silence?
Thanks. Okay.
Last call for questions.
And of course, we'll be available on Slack. I would love to get feedback, because this is far outside my comfort zone. And any ideas that you have, obviously we will be continuing to talk a lot with Matthew Guzdial, but if other people have ideas too, we'd love to hear them.
Yeah.
Right, cool. That's all. Thanks, Shiva, for the cool talk.